Today we're going to cover general linear least squares, and we're going to do actually 4 examples, and actually 3 of them are going to be examples we've already done. And the reason we're going to be looking at some examples that we have already done is we're going to see that they can all be solved using a slightly more general technique. Okay. So let's begin by getting out that x data. Okay, so we want the first column for the x's and the second column for the y's. Let's just plot it to remind ourselves what this data looked like, x, y, and we'll use the asterisks. There we go. And if we go back to editor, we can hit run. All right, and looks good. And now the really interesting thing is when we were working on, say, this CO2 example, we came up with a matrix that was based on partials. Okay, so that matrix can actually always be formed by doing Z transpose times Z. And that matrix B that we were working with before could be formed by doing Z transpose times the Y data. Okay. So what we'll end up doing is we'll end up still solving for our coefficients, but the way that we're going to do that is we're just going to do Z transpose times Z backslash Z transpose Y. Okay. And I encourage you to go back and actually verify that this is true. Look at your matrix A that you computed and then compute Z transpose times Z and see it's the same matrix. The one that, again, this is the one that would have been filled with all those sums. And we got it from taking partials. And this was just the other side of it, also filled with sums. Okay. All right. So let's go ahead and set up this matrix Z. The question is how are you going to set that up? Okay. Well, you first need to identify the basis vectors for the type of function that you're trying to create. So let's start off by just trying to fit this to a linear equation. So y equals, how about a1 plus a2 times x. So let's maybe say fit to data. Okay. And let's see what our basis vectors are going to look like here. Okay. And if you're thinking about linear algebra here, yeah, our basis vectors are actually functions. So what linear combination of functions will create stuff that looks like this? And the answer to that is we'd have 1 and x create these types of things. Okay. And so all the matrix Z is you're plugging your data into the basis vectors. So if you plug in x into this, well, that's just going to be a bunch of 1s every time, because right there's no x's in this first entry. So I'm going to say zeros. Or sorry, not zeros, how about 1s? Okay. And you can see that our x data and y data both have 61 entries. So I'm going to say 61 rows, 1 column, and then x. Okay. And that should be good there for z. Okay. And now we can go and we can just compute those coefficients just like this. We'll go z. Okay. Specifically Z transpose times Z, okay, backslash, okay, Z transpose times Y. Okay. And just to verify that this worked correctly, I want us to actually plot this. So we'll say, how about big Y is equal to A of 1 plus A of 2 times, how about big X let's say big X is equal to linspace, and our X data, let's kind of remind ourselves what that looked like. So this one was from 1959 to 2019. And actually, since this is just a line, why don't we just say 1959 and 2018. Okay. We'll just plug in two X values. It's a line. Okay. All right, and plot X comma Y, and let's see how we did. And if you're not seeing the data, it's because we need to input. Hold on. Let's go put that up here. There we go. So it seems to be fitting it okay. Or I should say fitting it pretty well. Fits it just as well as it did the first time we tried this. But let's try and now fit this data to a quadratic. Okay, and see, that we can have almost the same code here. We need to make very few changes. Okay. So let's go ahead and copy this code and start example 2, which is really going to be, again, the same, other than this time we want to fit it to a polynomial that looks like this. We'll have a plus a 3 times x squared. And so to make polynomials that look like this, we're going to need one more basis vector. We're going to need x squared, okay? Which means in this Z matrix that we just created, we're going to want to do x squared. Okay. See what else we need to change here. And also when we go to plot this parabola here, we're going to want plus a of 3 times x squared. Okay. And just to make the parabola look a little bit smoother, I am going to actually use linspace here now. And we'll go 1959 to 2018 still. But let's just put in some more points. Let's maybe do 50. So all we changed was we needed one more basis vector because this was a quadratic. And so we input that here in the matrix Z. Okay. And we plotted a few more x values. Okay. Okay. And then added on the last term to this equation here. Okay. Let's take a look. Okay. So let's see what our error is. It's saying in line 16, and that is for good reason. Let's make this a capital X, and since we're plugging in a vector in for X, let's also put the dot there. Okay. And if I were to make this a little bit bigger, you might be able to tell. It looks like the quadratic fits this even better than the linear model did. Okay. Okay. Now let's go to 3D and try this out. Okay. So this will be the example from yesterday that we'll look at here next. And I'm going to actually just copy and paste the code again. But I do want to make one little change. We're going to be using a different data set. We're going to be using the wave height one from yesterday. So we need to go in and import that. Wave height. There we go. And it looks like all the right stuff is highlighted. Okay, and now we have a third variable, z, so I'm going to say z equals data, and I want the third column for that. And if we're plotting in 3D, we need to use plot 3 and add in the z there. Next is what we'd like to do is we would like to figure out what this equation should look like. So this is the equation of a plane. So we should have a constant plus a constant times x plus a constant times y. So I just change this last basis vector to a y, and I'll change it here as well. And let's make just a couple more changes. So for one, this should be a y now. It should be a y now. And that also means we'll be using surf. Let me fix that. So we're going to have an x, a y, and a z. And that means that this equation here is probably going to be z equals something, right? So z equals a1 plus a2x plus a3y. It looks good. We need to set up our x's on here. Let's go and see what the x's look like in the data set here. So the x's go from 5 down to 50. Okay, so we only need to go 5 to 50. Let's just take 10. And then let's check out what the y's are looking like in that data set. I see 10 up to 60. So I'll do linspace (10 to 60). And then we need mesh grid. Okay. Which means I'm going to rename the big X and big Y above here in a second. I'm going to just name them X0, Y0. There we go. And then we can do mesh grid X0, Y0. Suppress that and that. Okay. So I think we have everything we need here. Let's go ahead and hit run. But before we do that, maybe let's just recap what we've changed. Okay. We have a new data set here. It has a third variable, so we needed to pull that third column out. We use plot3 rather than plot when we're trying to plot in 3D. Okay. We had to hold on because we're going to make another plot later. We formed a matrix out of our basis vectors. And we also computed all the coefficients we needed. Okay. We set up the x's and y's we want to plug in, and I'm actually seeing that I need to say how many y's I want. How about 10? This set up the grid of x and y's that we're going to plug in to this multivariable function. And then finally, surf should actually give us the graph of that. So let's go ahead and run. So editor, run. Okay. So let's see what the issue is here. So there is one more change that we need to make here. This 61, this came from our previous example. We had 61 elements in the X data and 61 elements in the Y data in the previous example. Well, that is not the case this time. It's 49. Okay, and I can see that over here in my workspace. That in fact X, Y, and Z are all 49 by 1. Okay. So let's see if that fixes, if that gets rid of our error. Okay. And it sure did. And just like you may remember yesterday, this is not the perfect model to use for this data since it's curved, but it doesn't do the worst job. Okay. It fits it okay. All right, and we're going to do one more example using this general technique. Okay, and this one will be a little bit different. Okay. Let's go ahead and click over and see what we have. Okay. So we have this data set. Okay, and I made it a small one so that it'd be easy to type in. And we want to fit it, or fit a function to it that looks like this. Y equals a constant plus a constant times sine of 1.5x plus a constant times cosine of 1.5x. Okay. So do notice, though, that this is a linear combination of three different functions. Okay. What would those functions be? Well, if we were to write a basis here, we'd have 1 again for the constant terms, right? Because you'd have a1 times 1 will give you this, plus a2 times sine of 1.5 times x. And then lastly, a3 times what function? And that would be cosine of 1.5 times x. Okay. All right, now, if these were all being multiplied, okay, then maybe we could take the natural log and linearize it. So that way we could use the technique that we're about to use. Okay. Or we'll look at another technique Monday, which will cover how to perform linear regression on things that aren't linear and we can't linearize them. Okay. But let's go ahead here and set up our matrix Z now that we know what the basis looks like. So we're going to have our ones. Okay. And I'm actually just going to count. We have 1, 2, 3, 4, 5, 6, 7, 8 elements in each one of these vectors. So I want an 8 by 1 of ones. I want sine of 1.5 times x. Okay. And do note that when I type in this, it looks like it is just a single row vector, but x itself here is a column vector. We're plugging a column vector into sine. So what's going to result is a matrix Z. Okay? Not just a vector, but a matrix. Okay. So there's Z. And then if we want our coefficients, okay, we could do the same thing. A equals Z transpose times Z backslash Z transpose times the output here, which is Y. Okay, which actually reminds me of something really important, and we're going to stop this example for a second and go back to our other one. So this should always be the output here, right? Like this was Y equals something. Well, over here with our general linear least squares, when I wrote our A in here for this 3D version, this should have been Z. Okay, should have been Z. Okay. And do note we're using big Z here as something different, but yeah, we should have been using the wave height data, not the wind duration or wind speed. Okay. Let's go ahead and run it. Okay. Still looks actually pretty similar, but it does actually look like it's fitting it a little bit better. Okay. See, if you remember, there weren't quite as many dots up top. Almost all the data was below the plane. Yeah, that looks better. Okay. All right, let's go back to example 4 here. Okay. And let's go ahead and set up our equation. Okay. So we are going to have y equals a of 1 plus a of 2 times sine of 1.5 times x plus a of 3 times cosine of 1.5 times x. And just so that this looks smooth, I'll probably change those little x's to big X's, and I'm going to pick more than just 8 points. Let's go, let's just say 0 to 5, and let's do 30 points. Okay. And one last thing, I said what I was going to change in this equation here, the little x's to big X's. Okay. See, to see how we did though, we're going to need to actually plot all this stuff. So let's say plot x, y, and hold on. And then we will plot this stuff here as well. Plot x, y. Okay. And let's make sure that the other one is just an asterisk. There we go. Let's go ahead and run it. It looks like we made one little typo here. This should be actually maybe a couple. This should be big Y and big X and big Y. Let's give that another go. Alright, and it looks pretty good. I could have maybe used more elements in big X, because I see that it's not perfectly smooth here, but it looks pretty good.